So this makes this the square root of 72. And so putting it into square meters, and we end up with something magical. Let's see, dividing by a bigger number, 1250. What do we get? 1250. 1250. Units? All right.
What is that negative?
Magnitude.
Oh.
The negative is telling us direction. We're going to take that into account in a moment. Again, when you're using the minus signs or trying to figure out direction, you either think through it or play strict adherence to the math. We're not doing the strict adherence, so we have to think through it. I know it's going to be a negative I hat, negative J hat. Nope. All right, so we have this 1250 meters per coulomb. I know it's going off in that direction, 1250 newtons per coulomb. I'm going to break it up. I have similar triangles here. I should actually draw them. I know that's 6, that's the square root of 72. Call that theta. So I get 1250 times that angle there is I was hoping for different colors there. I guess it's randomly giving me colors. So 1250 cosine of theta, negative I hat, minus 1250 sine of theta, J hat.
For these types of triangles, will it always be cosine with a negative number? And then,
No, it's because that negative right there.
yeah.
No, I know it's going that way in the negative I hat direction, so I think through that and I just put it in there. And so cosine of theta is, well, it's a 45, 45, 90, so negative 1250. And let's see if we can actually change colors here. Times square root of 2 over 2, I hat, minus 1250, radical 2 over 2, J hat. Or if you don't like that, 6 over the square root of 72.
Why is this one, if I'm remembering right, subtraction in the middle and the other one was addition?
Because the first one is going into, it's a second quadrant.
Yeah.
So my J hat is up, so the J hat is
It's just
just
direction.
positive. Pardon?
Based on where it's going, that's
Yes.
changing?
Oh, absolutely. So we just do one of them, I'll do the other one.
Negative 888 or negative 883.88.
Newtons per coulomb. I had, and second one, I'm gonna say somewhere around negative 884, maybe just a little bit less than that.
Yeah, down that right.
Is that right?
Sure is.
These are what you do in your head. Now, this is the hardest part. We've done the hardest part at this point, but we're not done yet. Questions to hear, Ethan?
With the same method, would it work, like, to multiplying it by 6 divided by the square root of 72?
Yes, it should. If it does not, then either there's a Carroll's error or math people have lied to us. Should be 0.707 something. I assume that's what you're getting. All right. Now, the original question is, what is the electric field at point P? This is what we're finding right here. And so we need to add them. I have EP plus, I have EP minus. And so the sum, EP plus equals EP minus equals negative 883.9. I had minus 883.9 newtons per coulomb for J hat. And add. One, carry the 1, 4, 4, carry the 1, negative. People can chime in whenever they want, instead of watching me do math the way we did in elementary school. 13, 4, 39, 17. Well, I'm sure the international fans would love watching me do that. We're about to use these numbers, so it'd be nice if we had confirmation that it's correct. I'm not quite sure why it's taking that long. It's correct. It's correct. Okay, thank you. All right, so this is EP. Let's see if this makes sense. Nope, just that's where I want. Put it down somewhere. I know that EP positive is bigger than EP negative, the magnitude of EP positive is bigger than the magnitude of EP negative for the reason that was outlined earlier. If I add them graphically, so I've got a vector going like this and a vector going like that. If I add them graphically, I end up with a sum in some particular color. Oh, it actually behaved. So it is going off to the left. It's the second quadrant, so I would expect it to be a negative I hat and a positive J hat, which it is. The horizontal magnitude is bigger than the vertical magnitude, which it is. So I feel confident that we've done something right at least. That answer makes sense.
What is that symbol for the subscript on the bottom?
Down here,
Yes.
that's a P to indicate the electric field at point P. Questions to hear?
Why do we use that triangle to find the point P? Like, where do we start that triangle to find it at point P? Is it at the bottom right of the first triangle?
Wait, sorry. That triangle right there,
Yeah, like what vector?
that, I was adding these two vectors here.
Okay.
I tried to be more realistic in the length of them. Here I just sort of generically drew a line. But I know that this one is bigger than that one, So I may try to do it that way.
Now, what if you started with the shorter one first in your drawing?
When I added them,
Yes.
commuter property holds. So if I started with a smaller one, we got that, and then the longer one.
Okay, that's interesting.
The order should not matter. Other questions? All right, so let's make it official. I'm done with chapter 18, whatever the first chapter is. I think it's 18. Done with chapter 18. So next Wednesday, which is the 24th. So 1/24. Master set 2 is due. And homework quiz, oh, not 2. Where you were. Hopefully it's not an issue to have them both on at the same time. All right, for those who are not familiar with my quizzes, there are certain textbook homework problems. Now again, the numbering that I have for the assigned problems is different than what I think the textbook has right now. So to find out what is the actual problem, if you look at the solutions, I have the actual problem listed there. So I'm gonna take 2 of those questions, change the numbers, that'll be the quiz. You can practice them all you want, come in, the numbers will be different, but other than that, you should be very polished in solving those. If you like surprises, and like taking a really long time sometimes, I guess you don't have to look at them. My recommendation is look at them. Some of you know what I'm talking about. Masters at 18, also under coursework, there should be a document that's something clever like chapter 18 master set. Click on that, that is something that is to be submitted, handed in. With answers. In case you were thinking, oh, I'll just print it out, hand that.
So, when we said that the electric field was created by those 2 charges, how does that happen?
How does a charge create an electric field?
Yes.
That is an incredibly fundamental question.
We don't know. Yes. Witchcraft.
There we go. Chalk it into how do we know electrons are real? Well,
Got it.
if electrons are real, if we did this, this will happen. We do this, this happens, so we go, okay. So there's some supporting evidence. It doesn't prove it, it's just supporting evidence. Science never proves anything, it's just, you have a theory. If A is true, then B will happen. So if A is true and you do B, C will happen. So you do B, C will happen. Evidence, not proof. That will book at home that are partway through, well, electrons aren't real. And that's basically the premise of it. All right. Now, all of this vector stuff is fine. However, what about the scalars? Is there a way of looking at this exact same thing except with scalars? Yes. So let's start out with the big scalar? Energy. More specifically, because kinetic energy is not specific to anything in particular, other than just mass and speed. Yeah, it's been a while. Let's do it. In unison. What's the formula for kinetic energy?
1/2 mv squared.
Yes. Now, some people did not open their mouths, and I'm expecting next time you will. And for the rest of you, enthusiasm. For every conservative force, there exists a potential energy formula. That's the shorthand notation for what I just said. So, for example, gravitational force is conservative. And so there's two potential energy formulas, mgh and negative g m1, m2 over r. That would be the potential energies. The elastic spring force is conservative, and that corresponds to 1/2 a delta x squared. I think those are the only ones from 151. So now we have another conservative force, the electric force. The derivation does require calculus, so it's going to be, here's the formula. It looks all very much like this formula right here, just because if you think about the electric force formula, it looks a whole lot like the gravitational generalized force formula. The potential energy looks very similar too, except there's no negative sign in front, and you're using charges and the electrostatic constant. Let's see if the units work out.
Dr. Fox,
Yes.
is the second one the spring force?
Yes, the ideal elastic spring.
Is that 1/2 k delta x squared?
Yeah, yes. Where this K is the spring constant.
Can you say what the Hyler curves mean again?
With for every conservative force, there exists potential energy formula. Now technically, there is a mistake written on the board for the potential energy formulas. What is missing?
The plus z.
Plus some constant, plus some constant, plus some constant, plus some constant. Because technically, you don't really solve, when you do the derivations, you don't solve for potential energy, you solve for change in potential energy. So therefore, the potential energy formula could have a constant. All right, so let's just start out with a straight up plugging. Oh, sorry, we're gonna look at units. So I'm making the claim that my electric potential energy is equal to Ke Q1 Q2 over R plus some constant. I know that the units, so if I looked at the units here, and the units of the constant just need to be in joules. So I have joules, and I should have asked you, but you knew it. Units of Ke are Newton meter squared per Coulomb squared, times coulombs divided by meters. And what does that reduce to? Or to what does that reduce?
Newton meters.
Is a Newton meter a joule?
Yes.
In the context of energy, yes. When is a Newton meter not a joule?
Working kinetic.
I said work. Not work.
Kinetic.
not, no. Newton meter definitely is a joule with work and kinetic energy.
Momentum.
No. Torque. A Newton meter with torque is not joule. Sorry to spoil it, I'm sure someone is about to yell it out proudly. All right, so let's do a little bit of a plug and chug here. That's too much of a nuisance, so we'll just erase. All right. I have a 3 microcoulomb charge here and a -6 microcoulomb charge there. The distance between them will make 0.1 meters. And I'm going to make the electric potential energy equals 0 at R is equal to infinity. That's a common one that's used, but not always the one that's used.
What is, okay.
I have to somehow define what my value of C is. And so, if R is infinity, or for you math purists, as R approaches infinity, what happens to this fraction?
It's infinitesimally small.
All right, so since this is infinitesimally small, then when R is equal to infinity, the electric, and that's supposed to be an E there. The electric potential energy at that point would be equal to the constant, and so this basically is saying the constant is 0. All right, plug and chug. So UE is equal to 9 times 10 to the 9th times 3 times 10 to the, what is mu?
-6.
-6 times -6 times 10 to the -6 divided by 0.1, not squared, divided by 0.1. And if y'all want to be kind enough